Okay, so in this video, we are going to pick up kind of where we left off with the last one, which was with the derivative chart that we had here on the left. And just a very quick recap, what did we do last time was to think about, well, we sort of derived, I guess, the first few rules in the chart just by sort of some examples and by doing some kind of logical guessing, I guess. And what did we end up with was we ended up with, first of all, this chart in general is wonderful in that this is a very, very quick way now, right, of being able to compute or look up, I guess, derivatives without really actually having to do any work, right? So if you want to know what the derivative of sine of x is, you just say, oh, sine of x, oh, the derivative is cosine. Or you want to know what the derivative of x cubed, well, then that would be 3, right? N would be 3 if you want x cubed. So you say, oh, okay, over here it's 3x squared, right? 3 minus 1. So it's very, very good, right? This is practically no thinking, right? Which is fantastic in that regard. And who's here? I guess who's here in this chart? The first 3 rules kind of collectively together let us do any sort of polynomial type thing, so powers of x. If we want to do exponentials and logs, there they are. E to the x and ln of x are both right there. And then the last grouping is the last 6 in the chart, which are all of our trig functions. So again, you just immediately can know what the derivative is without having to use, this formula and this procedure that, let's be honest, none of us really want to have to do each time. So, but rest assured, that's where all of these came from, was, somebody sitting down with, cotangent and plugging cotangent in here and saying, oh, well, I did this, and then I did this trick, and I did that trick, and blah, 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 and eventually I got that. So, I'll be honest, even I have never seen all of these things derived, and who really cares? And that's what's great about a chart or a formula or whatever shortcut, is that, it's perfectly fine to use these and say, well, this is the answer. It's certainly, these are certainly true. And, how much merit is there in spending half an hour when you could spend half of a second, literally? So, okay, I will just remind you, though, that I will ask you to do, probably one on the first exam and probably maybe one on the final exam as well. I will ask you to do a couple the long way, in other words, using this formula, the f of x plus h guy. Just to have you have some sense of where these things came from. But apart from that, apart from those questions, which specifically tell you compute this derivative using the definition of the derivative. That's what this guy is. That's the definition of the derivative. So unless it says that, you should use this chart because, of course, it's fast and it's easy and it's sort of error-proof. So, all right. So what is what more is there? Well, if you look at the chart, we sort of have all the basic characters of the math story here. You've got, again, polynomials, you've got exponential, you've got log, and you've got trig. Okay. So if all we ever wanted to know is what's the derivative of literally one of these, I think there's 11 characters, yes, it's true. You immediately know the answer, and that's it. But in reality, in the real world, you're not going to necessarily always have exactly one of these 11 things. You might have some variations on them. So maybe instead of just doing, you don't have to necessarily write this down, but what if you wanted to know what's the derivative of, 5 times sine of x? Huh. Well, you know what the derivative of sine is. That's in the chart. And 5, that's a constant, so you know what that is. But what am I supposed to do when it's 5 times sine of x? And I'll leave us in suspense for a minute to say I'm not sure. So what am I supposed to do when I have, a number, a coefficient? I guess that's what 5 would be called, a coefficient, times a function. What am I supposed to do with that? Am I supposed to Well, I don't know. I don't want to make any speculation right now, so I'll leave that with some question marks. But the point is that, of course, that's something I might want to know. And technically, I don't know what the answer to that is, because nowhere in my chart do I see 5 times sine of x. I don't see it. It's not there. So I need something to be able to help me deal with things that are kind of in my chart, I guess is the unscientific way of describing this. In other words, things that are sort of variations on things in the chart. Well, I'd still like to be able to do those. But for now, I'm going to punt. I don't know what that is. And what are some other variations I might have? Well, how about if I just did something simple like adding, right? I mean, that's not crazy. What if I wanted the derivative of x plus e to the x? Well, again, right, those are both in my chart. But what am I supposed to do when they're added together? Do I do something crazy and completely different? Do I do something that's kind of, well, I don't know, right? The point is I don't know. Again, I don't have a rule in my chart that says, oh, if you have x plus e to the x, here's your answer. I don't have that. All right, and more to come. So, and other types of things. You know, what if I multiply them instead of adding them? What if I divided them instead of multiplying them? Or what if I did something, you know, just sort of altogether different, like, I don't know, plugged one function into another function? So these will all be questions, right? So far, these are all, I don't know. But I'd like to know, right? And so that's what the next several lessons are all about, or it will be how do I deal with these, I guess, variations or modifications on things that are in the chart. And to be honest, there aren't that many things that can happen. It's kind of one of these 5. I think I have 5 examples I just made up there. We'll have a rule for each one of these 5. And with a rule, now you can act sort of legally in terms of being able to say, oh, okay, well, I have a rule that says I am allowed to do blah, 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 so here we go. But without that, I mean, sincerely, the answer to each of these 5 questions is question marks. I don't know what the answer is. I maybe have some suspicions or guesses, but I don't really know, because none of these 5 things are in my actual chart. And I probably have said this before, I'll say it again. Charts or formulas or shortcuts or whatever you want to call them are wonderful and terrible. Wonderful for obvious reasons. Terrible, though, because when you're reliant on using a sort of cheat sheet of sorts, which this is, you have to use it very strictly. In other words, if it doesn't say you can do something, you can't do it. So it doesn't say what I'm supposed to do if I have x plus e to the x. This chart says what do I do if you have x, and it says what do you do if you have e to the x. But it doesn't say what to do when you add them together or multiply them or divide them. So I need more rules. Okay, so if anything, I'm hopefully motivated that much. So let me get rid of this stuff here. And say that I'm going to come back to this slide a couple of times. I think I've left myself enough room over here to fill in what are going to be 5. There's going to be 5 what I'm going to call derivative rules that are going to sort of accompany the existing chart of 11 sort of building blocks. I might call the things on the left more like shortcuts, whereas what we're going to eventually have will be 5 rules, derivative rules or laws, I guess you could say, that say, oh, if you've got a this, here's how you do it. Or if you've got something that looks kind of like a that, here's how you might treat that, and still be able to do the derivative in a relatively easy way. Okay, so we'll do at least the first couple rules in this video, and then we'll do, I think, the next couple in a separate one, and the last rule is the hardest one, so we'll have a separate video for that altogether. All right, so, and I'm going to come back to this chart periodically once we come up with our results and fill those guys in as we go. So hopefully that by the end of the next couple lectures, this will be filled in, the 5 rules, and then a sort of screenshot of this, or if you want to just write one on a piece of paper, it's probably not a bad idea, will sort of become your guide. This will be sort of your ultimate cheat sheet will then be to have this whole thing filled in, and that's basically your derivative helper. All right, so rules. Okay, so the first rule might be to deal, and we'll take these sort of in order of easy to hard. So so let's start with an easy one first. So what happens if I've got a coefficient? So this would be called the coefficient rule. Okay, so coefficients, you remember, it just is a fancy word for what if you have a number in front of a function. So typical example, I think this is what I wrote on the last slide, is what if you have something like 5 times sine of x? And I want to know what's the derivative of that. Okay, so, so we think about this, okay, so I want to do derivative of 5 times sine. Well, sine, I know what the derivative of sine is. The derivative of sine is cosine. And the derivative of a constant, which 5 is, would be 0. Well, hopefully you can kind of see right off the bat that if I just sort of naively said, well, I don't know, it's 5 times sine, right? I mean, it is, it's true. So maybe I just do the derivative of 5, which is 0. Don't write this down. And then I do the derivative of sine, which is cosine. Oh, but that would be 0. Well, saying something has a derivative of 0 means, if you remember from when we first started talking about derivatives, derivative means slope, doesn't it? So a slope of 0, we all know what that means. It means something is flat, right, or horizontal. Well, that's not good, right? Even if you don't have a graphing calculator in front of you, you guys, I think, remember sine of x is a wavy function, right? I mean, I won't draw it officially here for you, but kind of goes like that. That sure as hell isn't flat, right? So I don't think the derivative of that is 0. For the derivative of something to be 0, it's got to be literally just a straight line, a horizontal straight line. Okay, so that's obviously wrong. So I erase that immediately. So I can't just sort of, this is kind of underscores what I said a few minutes ago. You can't just sort of say, well, I don't know, I've got this thing in the chart and I've got this thing in the chart and I'm just going to sort of haphazardly throw it together, because you will end up with wrong answers most of the time. So, all right, but I still want to answer this question. What is this? Well, think about it. What would I do if I was to do it this sort of old-fashioned way, right? If I was to use this awful formula. What would I get, right? What would I get if I actually just attempted to do this and just attempted to fill this in? Well, for f of x plus h, so in other words, if this is f of x, right, this whole guy now, because the question is, what's the derivative of that guy? Well, that's f of x then, because this is, right, my formula says, here's how you do the derivative of f of x. So f of x is 5 times sine of x. So if I was to fill this in, I'd get, that would turn into 5 sine of x plus h, and then minus 5 sine of x, and it'd all be over h. Okay. But look at the top of the fraction. Obviously, in the top of the fraction, each thing is multiplied by 5. So I could factor that out, right? There's a 5 in common in the top. So I could pull that out, actually, and instead say it's really just this. Okay, so I pulled the 5 out in front, right, because it's 5 times that whole thing now. Oh, but what do you see in parentheses there? What you see in parentheses there would be exactly the derivative of sine of x. Okay, so if f of x was just regular sine of x, just sine of x without the 5 in front of it, and I'd filled into my derivative formula up here, if it was just sine of x, this is exactly what I would get, right? So, so what does it kind of look like I just did here? It looks like I kind of just said, well, if you have a number in front of a function, I think even though this isn't necessarily a proof, it kind of looks like, doesn't it look like the number part just comes along, and then I take the derivative of the rest, in this case, sine of x. Now, I don't want to have to do this, right? I mean, that's still not my friend. But now I can use the chart, because I know the chart tells me what the derivative of sine is, and I'll glance back at it for a second. The derivative of sine of x is cosine. So I think I would get 5 times cosine of x, because cosine of x is the derivative of sine. So let me write it up here too. So my answer would be that. And we can think about it by saying, just in English, right, the rule that I think we've just discovered is that the coefficient comes along, or in other words, just sort of gets carried over. And then what is it that I actually need is I actually need to do the derivative of the stuff that actually has x's in it. That I actually need to do the derivative of, but that's probably something that I can get just by looking at the chart. Okay? So I think we've got ourselves a rule here that would say the following. So here's the generic version. If you want to do the derivative of something that looks like a number times a function, then how do I do that? Well, the number part the coefficient should just come along and then do the derivative of the rest. Okay? So again, the number piece, the coefficient, that just appears in the answer. And then what is your actual work that you have to do is compute the derivative of the stuff that actually has x's in it. And again, for that, you can probably consult the chart or one of the other rules which we're about to describe. So, all right, so in many ways, this is sort of if I made you guess and said, what do you think you do when you have a number in front of something? This might have been what you guessed, right? It's not a leap of faith to maybe say, well, derivatives kind of talks about functions, so maybe a coefficient in front of it is just a multiplier. And indeed it is. So this is actually kind of one of these, I'll write it down as one of the rules, but it's actually one that you sort of are just going to use without really thinking about it a whole heck of a lot. But that's great, right? Rules that you don't have to sort of invoke actively each time, that just sort of occur naturally, that's even better. So, okay, so we'll add that rule to the chart in a couple minutes after I do the next one. All right, so maybe I'll just do one more quick one while I'm sitting here on this page. Let me erase this and just give myself some space. So if I just wanted to do one more quick one using just the rule without having to do all this other stuff, I might just say, well, what if you have, what if you want the derivative of something like 4 times ln of x? I say, okay, well, the coefficient rule, this thing we just discovered, says if I want to do the derivative, then a coefficient should always just come along. So the 4 should just be sort of carried over. And then what is it that I really need to do is just think about the derivative of the thing that has x's in it, which in this case is ln. Well, the ln of x, that's in my chart. The derivative of the ln of x, if you look back in the chart, is 1 over x. Okay? So that's my answer. Or if you want, it's probably easier to write it as just 4 over x. Right? That's what that is. All right, so it's pretty simple, right? This isn't a groundbreaking, amazing accomplishment in math, but an important step, right? And again, it's important to kind of emphasize, without a rule that says you can do this, you really can't, or you really shouldn't. But in this case, it's sort of like, okay, yeah, this is sort of what I think I probably would have guessed I could do, and the good news is yes, you can. All right, so that's the easiest, I think, of the, the easiest probably of the rules. So what's next? So in addition to being able to handle coefficients, I might want to handle something else which is very basic, which is what happens if I wanted to do the addition or subtraction. Whoops, oh goodness. So what happens if I want to be able to maybe add or subtract 2 functions or 2 or more functions? What would I do there? Okay, so again, let me start us with an example. So let's say you have something like x squared plus maybe tangent of x. Okay, so again, each of these characters is in my chart, right? X squared is in my chart, I know the derivative of that. And tangent is in my chart, I know the derivative of that. But what am I supposed to do when I want to do the derivative of the sum, or difference, as it turns out it's the same, of 2 or more functions? Well, again, you might have an instinctual guess, which might say, well, I don't know, do the derivative of each one separately and then add them. But we don't have a rule that says I can do that, so the answer to this question right now is I don't know what the answer is. I don't know how to do the derivative of one function plus another function. So again, without lack of, since I have no other, strategy in mind, I might say, again, just appeal for a moment back to our old friend, or frenemy is probably more accurate, which is this guy, the definition of the derivative, and say, well, okay, what happens if I wanted to do this where this now whole character, that's f of x, right? Because I'm trying to say what's the derivative of this guy. Well, if that was the case, if that was really f of x, namely the sum of two functions, what would happen? Well, if I filled that in on the right over here, what would I get? Well, I'd get f of x plus h, which says put x plus h in everywhere you see an x, which means here and here. So I'd end up with x plus h squared plus tan x plus h. Okay, and then I would do minus that whole thing, minus f of x. So minus x squared plus tan. Okay, all over h. Well, this is awful for many, many, many reasons. This is a disaster. But I'm going to do a very simple thing, which is to just reorganize. So let me put the tan stuff together and the non-tan stuff together. So what would I get? I'd get x plus h squared, and let me pull the x squared together with that. So let me group those two things together. And then let me group the tan stuff together. Okay, now these are still added together, right? I'm still doing this plus that stuff, so I'm still adding here. But I can break this into two separate fractions. That's legal. They're both divided by h. And now squint with me for a second. This is exactly the derivative of x squared. And this is exactly the derivative of tan x. Okay, namely, right, that this guy and this should look very familiar, right? The first circle here, that's exactly the derivative of x squared. We've done that derivative a whole bunch of times already, so that should look kind of familiar. And even the guy on the right, doesn't it just sort of look like my formula up here? But with tangent replacing f. So in that sense, it should exactly be the derivative of tangent. Aha. Well, now, two good things are true. One, I know the answer to both of these questions at the bottom right here. Because do I know what the derivative of x squared is? Well, I could do this awful algebra problem, I guess. But let's not do that, right? I have a chart for a reason. The derivative of x squared via the chart is 2x. And the derivative of tangent via the chart is secant of x squared. Huh. So what does it look like my punchline is? It sort of looks like what I did here is I said, if I want to know the derivative of the sum of two functions, this guy plus this guy, doesn't it look like I just did the derivative of the first guy and then added it to the derivative of the second guy? I mean, that's exactly what I did, right? And squint with me here for a second. If this had been subtraction, would this have really actually mattered? The only thing that would have been different is that the addition signs would all turn to subtraction signs. So that would be a subtraction, and that would be a subtraction. So there's really no difference if I had had subtraction versus addition. You would have gotten the same. I would have gotten the same thing. All right. So I think my rule sounds like if I want to do the derivative of the sum, in this case, or difference of two things, just do the derivative of each piece. Which, will likely involve the chart. And then whatever you've got in between, do that. If I've got addition, add them. If I've got subtraction, subtract them. Okay? So let me formally write that down for you then. So what does the rule actually say? If you want to do the derivative of one function plus or minus another function, the second function I'll just call maybe g of x. G of x is just some other function. If you want to do that derivative, just do the derivative of the first guy, and then add or subtract, wherever is appropriate, the derivative of the second guy. And in fact, you can do this with more than just two. If you have something plus something plus something, you could just do the derivative of each one separately and add. Okay, so In many ways, this is, again, much like the first rule, the coefficient rule, this is actually a rule that you kind of could have guessed, I suppose, right? If push comes to shove, you had to sort of say, how do I think I do the derivative of something plus something? I guess it's not a terrible thing to have guessed that you could maybe just do them separately and then add at the end. And the good news is that you can. And of course you can combine this with the coefficient rule. So maybe just to give you one more example before we move on. If I wanted to do something like, what's the derivative of something like 5 cosine of x minus, I don't know, the square root of x or something like that. Say, okay. Well, for starters, what is it that I'm looking at? Well, I've got one function minus another function. Okay, so the first thing I can say is, well, this is, would invoke, I guess, this new rule that we just talked about, the subtraction, or the addition and subtraction rule, which says if you want to do the derivative of something like this, just do each piece separately and then add or subtract at the end. So that's easy, right? I can certainly say that. I could say, well, I'm just going to do the derivative of each one of these guys separately and then subtract. All right. Now, to do the derivative of 5 times cosine, I could actually, if I'm really being careful here, I would say, well, that's technically a coefficient rule because I have a number in front of a function. So the coefficient rule would tell me the derivative of this, the coefficient should come along, and then I consult my chart to say the derivative of cosine, which actually turns out to be negative sine. Okay, so this is sort of, I guess, I don't know, more than 2 rules in one, I guess, right? I'm using the subtraction rule to do this overarching problem, and then within the subtraction rule, I needed the coefficient rule in order to do this first piece. Okay? To do the derivative of the square root of x, just remind yourselves, the square root of x is actually the same thing as x to the 1/2, because this is what you can actually now use our third rule in our chart to say, oh, x to the 1/2 should become 1/2 x to the negative 1/2. That's just our standard, this guy rule. Okay, so I think, go back to this for a second. If you want to clean this up a little bit, you can. This is the same thing as, it's just sort of handy sometimes to put the negative sign in front. Negative 5 times sine of x. There isn't much I could say about that. I would just sort of leave my answer like that. Okay, so let me flash back now and add those 2 rules that we just did to our sort of growing list now of the derivative chart, which is to say now we can handle 2 of our 5 sort of extensions. We have a coefficient rule, which says if you have a number times a function, then the derivative of that is just that number, that coefficient, and then do the derivative of the stuff with x's in it. Okay, and then the last rule that we just did handles addition and subtraction. Which says if you have one function plus or minus another function, the derivative, well, you can just take each one separate, take the derivative of each piece separately, and then add or subtract it appropriately. Okay, so and those again are those are the 2 easy guys, and are the ones that are, you know, kind of, you would think you can maybe do this anyway. And the good news is that you can. I don't want to spoil the surprise, but for our other 3 rules, it's not actually the case that you can just do what you kind of think or hope you could do. Unfortunately, things will start to become unraveled a little bit, and we'll need some other strategies. So, all right, so I'm going to stop this video and come back in the next one where we'll do the next two rules in this chart. And I'll always sort of try to come back to this chart again to build it up to be your sort of master list of derivative shortcuts. So, okay.